All right, it seems like I'm live. How you guys doing? I'm Alex, the entrepreneur. Thank you for being live with me. In this live stream, I'm actually going to go over the Yearn code. Specifically, I'll go over Yearn V1, which is not necessarily the most up-to-date DeFi application. However, it's a great starting point to do a code review and to just learn Solidity and learn how that works. So if you have any questions for me, I'll be reading the chat right there and I'll just go over that. I'm doing this experiment to see if there's any interest. Hey, Nias, how you doing? Great, glad to have you here. And again, if you have any question, let me know, but I'm doing this for educational purposes. I am not invested in Yearn, and I thought it was a good idea to just cover it because you may have heard the noise related to Ethereum DeFi development. And as such, I'm going to start by sharing my screen. I'm going to read all of your questions and answer them. And again, I'm going to go over Yearn V1, which you can access on github.com/Yearn protocol. And the reason why I'll go over V1 is because all of the code is in one repo. And a friend of mine, colleague of mine, Tom, actually taught me most of the code. So I have to give him creds for that. And as such, I can actually make an entertaining argument. Again, if you have any question, let me know. If you're developing your own Solidity project, just send me the code in the chat and I'll be happy to check that out. I'm going to go in the contracts folder. I'm also seeing that there's an interface folder. Both of these are fairly interesting. We have let's see what we have for interfaces. Basically, for interfaces, we're going to have all of the external smart contracts that Yearn will be interacting with. And for context, if you want to find the V1 version, you can go on v1.yearn.finance. And that way you have an understanding of what the product looks like. And I'm going under the vaults section to just show what it is. So this was literally the catalyst of DeFi summer of last year. So I just think it's a great idea to cover this before jumping into more advanced concepts. Obviously, there's a Yearn V2 now. So if you wanna check that out, this is the most recent version. However, this is way more advanced, way more complicated, and it takes a while to wrap your head around it. So again, we have this interface folder, which simply goes to show the way for us to interact with other protocols. I'm going to open the compound token.sol randomly just to show one. And we can see that this is just interfaces, which is a way to specify how to interact with the rest of the code. I would love if there was an easier way to just import code from other GitHub repos without having to copy paste all of this. As when you actually start developing in Solidity, you actually end up like the simplest decision is always to just copy paste. But that means that we have all this additional code which is not particularly useful. Thank you, man. Yeah, I do have a beard, and I'd also have a barber that takes care of it once every couple of months. So thank you for the compliment. And yeah, basically in terms of interfaces, we just have ways to interface with other different protocols. And that's because if you don't know it, Yearn is basically a tool or a set of smart contracts that automates yield farming, which means that you put your cryptocurrencies such as ETH, WEF, or DAI into this vault. And then what the vault does, it uses strategies to invest these currencies into other smart contracts. As if you look at the interfaces, you can assume that it's going to invest into Aave, Compound, Cream, Curve, dForce, Maker, Uniswap, and itself, I guess. And it's going to do that again to automate yield. If you're not familiar with any of these protocols, drop a comment in the chat or in the comments, and maybe I'll also cover those. I thought, this was like an interesting application of these ideas. But if you're completely unfamiliar with Aave or Compound, You can literally just Google them and you'll find that these are decentralized lending platforms, which basically means that you can take, again, your currency, DAI, USDC, etc. And basically they will lend them automatically for you, and they will share the yield with you. And you can see that the yield is going insane today because I'm in the AMM market actually, but Aave is actually going to incentivize more deposits. So you'll see that the numbers will go insane. How to make a shitcoin like SafeMoon? I love that question. And if you stick around for a few more minutes, I'll actually talk about SafeMoon. I think it's an hilarious project with 400,000 Twitter followers. That has to be like the most hilarious outcome. But yeah, I wouldn't put a dime into that project, even if they paid me to do that. And that said, this is Compound. Compound is another lending platform. You can click on markets and see the available currencies. And basically, again, you can just put your current cryptocurrencies into Compound. It will lend it for you. It will earn an interest and give you that interest. Now, something interesting that you'll see here is that each market has a percentage. It gives you a supply APY, which means that it's an interest rate that you get for just putting your dollars here. And then you have a distribution APY, which is the percentage you get from, it's basically the extra value that you get in Compound token, which means that you get paid in a different token from the one you put in. And you specifically get paid back with this Compound token, which fundamentally, if you go on governance, you'll see it, but fundamentally it allows you to basically vote on the future of the protocol through what is called a, I guess through, because Compound is now a DAO, which means that it's a decentralized autonomous organization. And that means that owning the token means that you own a part of the protocol, basically. And as such, you can vote on its future. So that's the point of the token. But for those financially savvy, the token is also another way to get more money, basically. And as such, there are tools such as Yearn, which will auto-invest those for you. Again, in a few minutes, I'll talk about SafeMoon. We'll actually read the source code, and I guess we'll talk about it. But I want to make sure that you guys understand that for some people, the Compound token is a voting token, and as such, it's a tool that allows you to decide the future of the protocol. It allows you to interact with the developers and have a say in the protocol. And for other people, it's a speculative asset. And they will just get the token and sell it back as a way to have more dollars. And so that's basically what Yearn will do. And so I guess that leads us into why we have the interface here for token. And it also leads us to why we have an interface for Uniswap here. And the reason is because once you get your Compound token, you're gonna swap exact tokens for tokens, which is the act of taking your, let's say, taking your Compound token, swapping it into USDC, for example, and as such, earning that extra USDC, which you can now use to earn more Compound. Something else that you wanna learn about is the fact that if you look in the markets, let me see if there's the distribution UI for it. But fundamentally, since these markets are subsidized by the Compound token, this means that there are situations in which borrowing currency, borrowing a USDC, for example, will actually pay you back in Compound token. So that means there are situations in which it's worth it for you to take a loan in order to get more Compound token. This is something that I've read from Arbing Sam. So I want to give the credits. You can check this blog called sampristi.com, which talks about this idea. So this guy's genius guy in the act of finding arbitrage opportunities. And this is called basically I guess a yield arbitrage. But what it means is that if you pay attention to these numbers, you may actually find a situation where borrowing has, in this case, it has a 3.7% rate, which means you pay 3.79% to borrow, but you may actually find that sometimes you'll find a negative rate, which means that you actually are being paid. Let me see if we find one, but basically you're being paid to, there you go, you're being paid to borrow Compound token. You get paid 7.27%, which means that the act of taking a loan of the Compound token effectively pays you in this compound token. So if you value the compound token or you want to convert it to USDC, you would actually have an incentive to just borrow that out and take that interest off of it. Now, obviously, you have to factor in gas, you have to factor in a lot of stuff. And again, that's why a tool such as Yearn even exists. It's literally because they will automate this process for you and they will bulk those transactions. So now that I'm going to dive deeper in the code, hopefully you have an understanding for why Yearn exists and what it actually does. And again, we're looking at V1 because it's much simpler. I am more equipped to talk about it, and it just there's all of the learnings are here, and maybe we'll look at V2 later. And if you're interested in me talking about SafeMoon early, and we got a second person commenting about SafeMoon, I guess I'll jump into the SafeMoon debacle first. But otherwise, I'll just get started, and I'll start with vaults. These are going to be our free keywords for Yearn: vaults, controllers, and strategies. Those are the free keywords you want to keep in mind. And a vault is the place in which you deposit. So in this case, you can see the vault here. This is the place in which you will do a deposit. Then you will have a controller, which will manage the assets of the vault. And lastly, you have a strategy, which is a set of actions that the controller will take in order to get that yield. So I'm going to go in vaults. And we have 3 vaults currently: Y delegated, we actually 4, curve vault, Y delegated vault, Y vault, and Y WEF vault. So if we look at this, we see the if vault, which is actually this one. We have the Y WEF vault, which will be this one. Then we have the curve vault, which I'm not seeing. Perhaps there are no balances in it. Yeah, so basically we have all of these vaults. And we're just gonna talk about one because the source code is gonna be very similar. So I'm gonna open the YWEF vault, and we can do a quick comparison to see if there's any quick difference between the 2 vaults. Although it really doesn't seem to have. Basically, it seems to just be more complicated because we are dealing with WEF and if. And if you're not aware, if is the way you pay gas, the way you pay for transactions in the Ethereum blockchain. And WEF is the wrapped version of ETH, which basically means that it's the ERC20 version of ETH. And the reason why you would need a ERC20 version is because developers will have to write specific code to handle ETH, while all of the code that handles a ERC20 will be the same for any ERC20. Basically, that means that anytime you have to actively support ETH, you have to work twice as much for very little benefit, while you would be just better off wrapping that ETH in the first place. So let's look at this. Let's actually just look at the Y vault, which should be the DAI vault, and which is going to be simpler. It basically uses a ERC20 and allows to deposit. We see that we're using safe ERC20, where the safe, anytime you see this stuff, by the way, especially when you see these Open Zeppelin appear, that means that if you literally Google Open Zeppelin, and in this case, you will Google safe ERC20, you will find the documentation for it from the Open Zeppelin docs, where Open Zeppelin, I'm not sure who financed it, but it's basically an open source collective of contracts that basically define the standard. So anytime you see a contract written by Open Zeppelin, you can trust it by default. And anytime you see a contract that is not written by Open Zeppelin, you probably will have to read it line by line. That said, you should also read the Open Zeppelin contracts, but they basically pave the way in writing these contracts. And so the main difference between the ERC20 and the safe ERC20, as we can see here, is that the safe ERC20 will throw on failure. So a normal ERC20 may perform an operation, let's say a send, a transfer, and approve, and that operation may fail, and that operation may simply return false. And that means that unless you're checking for the outcome of that operation, your contract may continue executing. And if you ever written anything in Solidity, you know that you would rather have the contract revert, because otherwise you're bound to lose money. And the simplest example I can give is that if you have an ERC20 operation, and then you have an operation where you are, let's say I'm sending you some money, then The fact that the ERC20 operation doesn't fail and it doesn't revert will mean that somebody can just literally just press a button and take all of my money systematically. So that's why you will use the safe ERC20, and basically you get that behavior without having to really think about it. Like, it just makes your life so much easier. So again, safe ERC20, that's why it is. And open Zappeling, again, you can check it out, and it basically makes your life so much easier. We also have address for address. If I'm not mistaken, it's a way to verify, we'll see it later, but it's a way to verify addresses and to check if they're a contract. It's basically a set of utilities related to addresses. And then we have the safe math, which fundamentally ensures that you don't get overflows. And that's because like if you look at any number, any digit in Solidity, you'll see that we don't have decimals. And that also means that if you subtract a number with a high enough number, you'll actually go, you would expect to go in the negative, but what would actually happen is you would overflow. And the act of overflowing basically will throw off your math. And if you ever played GTA 5, that also explains why the maximum amount of money you can have is something like 2 to the power of 32. And that's because if you add an extra digit, you're just going to lose all of your money. Next up, we have an ERC20 public token. We don't know what that is. We'll figure it out. We have a min and a max. We can see that it's 9500 and this is 10,000. And I know that this is used to have a something like a 95%. We'll figure that out in a second. We then have a address related to governance, and then we have another address related to the controller. We have our constructor, which receives a token and a controller, and then it calls a constructor, which has been brought by, again, the Open Zeppelin contract, which will call ERC20 detail, specifying the token name. It basically will specify a name prefixed by Yearn with a space, and then it will set the token symbol to a token symbol with a Y. And if I'm not, at this point, I'm assuming that token is going to be the address, the address of an actual token that exists, such as USDC, DAI, etc. So this is a way for you to programmatically fetch the data from that token, because we are casting. This is the act of explicit type casting of the ERC20 detailed type onto the underscore token address on the token address. And then we're getting the name property here. So that's what's happening here. And lastly, we also get the decimals. So fundamentally, the token we're creating here, when we set up the Y vault, will have the same amount of decimals as the its counterparty, as the ERC20 counterparty, and it will then have a symbol that is very similar and prefixed by a Y. Let's see what else we do. We assign the token to ERC20 of underscore token, and that's because the token up here is a ERC20. So this is done through public. However, if you're going to be doing this in a newer version of Solidity, something like 0.7 or 0.8, you could actually use the immutable keyword, which ensures that this token can never change. I don't believe that's a security vulnerability unless there's actually a situation in which the token gets changed. But again, it just would make an auditor safer to have an immutable token. Next up, we have governance, and it's set to message.sender. This is literally how the majority of rug pulls are done. So we definitely want to check where the governance goes later, because this means that the owner of the contract is the person that created it, which is completely fine as the starting point. But if you are, if the protocol is suggesting that they're going to do a DAO, or they're going to decentralize, they're going to issue a different type of governance, this is basically a classic attack vector, because the one person that owns that contract is the one person that can do anything. And if I'm not mistaken, that was at the time that was a multi-sig with 9 signers, and you can find that in the docs as well. Next up, we have the controller. The controller is being set to a specific address. So that means that this Y vault will be deployed after the controller is deployed. Let's keep that in mind, but let's also continue. We now have a balance function, which basically will get the balance of the token, and then it will add the balance of the controller. We can see here .add iController controller of balance address token. So something that is particular here is that For some reason, I'm assuming under, but the developer decided to set the token to be a ERC20. Basically, they casted it to the specific contract type, while they didn't decide to cast the controller. I'm not sure if they ever will use the controller as an address, but that's something that is, it's just a particular styling coding convention. But basically, it's also very flexible though, because that means that anytime you need the address, you will just use the controller variable. And anytime you need the contract, you will just cast the contract like so. Next up, we have set min, which can only be done by the governance. And this is an indicator of some sort of boundaries and checks. That's not a bad thing. I believe that an even safer approach to this would be to also have a time lock contract, which means that anytime you want to make a change, you have to wait some time. But this will basically set this min variable, which we'll see what it does. Then we have the governance. This is the act of proactively losing access to the governance or giving it to somebody else. This is one of the most dangerous operation, because if the owner of the contract sends the ownership of the contract to somebody else, then that person may be able to withdraw, change variables, etc., etc. And the act of burning your keys is the act of setting the governance to the address 0. That's how you burn your keys. If you set that to 0, nobody can ever access that code unless you crack all of cryptography, in which case you will be concerned with that, not so much with losing access to this contract. Next up, we have set controller, which again is ruled by governance, and you simply set the controller to a different address. Here we have available, and we also have a comment. Custom logic in here for how much the vault allows to be borrowed. Sets minimum required on hand to keep small withdrawals cheap. And so that's something that if you followed Andre Cronio's work, you'll actually hear about that. I think in the FTX podcast, I'm not sure if the second or the third podcast, he talks about this idea. And the idea is that by having a float, by having an amount of currency that is not invested, you can make it so that small investors can withdraw without having to go inside of all the pipes and withdraw all that stuff from the other protocols. And so that just makes it really cheap, and it's just a nice thing to do for the small cap investor, considering that gas is already very expensive. So that's basically going to check available, and it will basically multiply to min by max. And again, we saw that max is 10,000, and we saw that min is 9,500. So to you as the developer, this is how you do percentages. You just do 10,000 and 9,500, or you can do, in this case, you could cut a 0. Although I believe Aave will do 1,950, while Yearn adds an extra 0. There is no difference, just something that I've noticed by reading their contracts. And you always multiply first. That's something that Tom reminded me. Shout out to Tom. If he ever wants to do a live with me, I'd be happy to have him. But basically, you always multiply first and you divide later, because if you ever divide first, you may actually end up rounding out stuff, or you may literally underflow or just ruin your math. So that's why you always multiply first in Solidity. Next up, we have a function called earn. Let's see what it does. It's going to get the balance here. It's then going to call safe transfer to the controller. It's basically going to send funds from the vault to the controller. And it's then going to call the earn function on the controller. So this basically gives us a clue as to the fact that this is a vault, and this is literally just a place where you put your cryptocurrency in. But then we have a controller which will do the heavy lifting. So we'll have to definitely check this in the controller code at a later time. Next up, we have deposit all. Deposit all is going to deposit the balance of the message.sender. So this seems to be like a utility to deposit everything. In a normal UI, you will just type max and then input that. I'm not sure why this is here, but that's okay. It's not hurtful or dangerous at all. Next up, we have deposit. And actually, let me see, deposit. Okay, so this deposit all is calling deposit, which is this function, and it's on the message.sender balance. Okay, so now we have the function deposit, and as you can see, some stuff is happening. It's not simply minting shares and leaving it like that. So let's see what happens. We see the balance here. which we already checked. Did we? Actually, not sure. Balance, there we go. Yeah, we checked balance, which is equal to all of our balance in here, plus the balance on the controller. Then we check before, we've taken the balance of address this, so we get the balance of this contract. Then we do a token, we do a safe transfer from the person requesting the deposit to the contract for the amount specified. And then we check the after. The after is equal to token the balance of address this. So basically we just get the balance after the deposit. We have before the deposit, after the deposit, and amount is equal to after minus before. So so basically, and I'm actually not sure about the security implications of why you will do it this way. Maybe there's something else here, but basically all we did is we deposited and we got the amount that we deposited by a subtraction instead of just trusting this amount value. We're not trusting this amount value. We're actually doing it through the subtraction. Next up, we got shares set to 0. If total supply is equal to 0, where total supply is a function that is already given to you by the Open Zeppelin code, and it basically tells you all of the amount of your ERC20 that you have, and it says that if it's equal to 0, then shares are going to be equal to amount. So there's going to be a 1-to-1 ratio between the shares and the amount. Otherwise, shares are going to be equal to the amount multiplied by the total supply, where total supply is all of the shares that represent the vault, and then we're going to divide that by the amount in the pool, which is equal to balance. So basically, this is a way to represent fractional ownership, and that's what's happening. And lastly, we get the mint that will assign those shares to the owner. Next up, we have withdraw all, which is a way to withdraw everything. And we also will have to check our withdraw function. We have also harvest here, which has a comment saying that it's used to swap any borrowed reserve over the debt limit to liquidate to token. Let's read it again. Used to swap any borrowed reserve over the debt limit to liquidate to token. We're going to swap from the reserve that we borrowed over the debt limit to liquidate to token. So it's going to get you the token, but it's going to do it on the borrowed reserve over the debt limit. So first of all, it can only be done by the controller. We require that the address is different from token. And I believe that's because we don't want to basically get rug pulled. There's a way to liquidate your token to yourself, I guess. And lastly, it's going to do it's going to call on reserve, and it's going to do a safe transfer to the controller for that amount. Borrowed reserve over the limit. I'm not fully sure I understand this, but we'll probably see this happen again. Next up, let's see the withdraw. As you can see, there's no rebalance implementation for lower fees. That means that this will literally just try to withdraw whatever is available. And only in this case, we're going to have to do more work. So R is equal to the balance of this contract, which, as we said, is the everything in the contract plus the amount in the controller. Then we're going to divide it by the total supply. So basically, this gives us a percentage ownership. Then we're going to burn the shares. And since we're using a safe ERC20, burning the shares, you can't burn more than that. Although I kind of believe you can't burn more than that even in the non-safe version of ERC20, but don't quote me on that. Next up, we have B is equal to the token, the balance of this address. Basically, we're getting, again, the balance that we have. If the balance is less than R, than what we need, then we're going to have to do a bunch of stuff. We're going to do R.sub B. So we're just going to get what we need to withdraw, because we're going to do it as a subtraction of the total amount that we need to withdraw minus the one that is already liquid. Then we're going to get the controller, and we're going to call withdraw on the controller for the withdraw amount. So again, we're going to have to check what the controller does. Shortly, we're going to do that. Then we have the after, which is simply this way of rebalancing it. So checking what the new balance is, token the balance of this, and then the difference will be equal to after dot sub b. And then if diff is less than withdraw, r equals b dot add diff. If the difference is less than the amount that we needed to withdraw, then r is going to be equal to b dot add diff. I'm kind of confused by this, to be honest. If the difference is less than the amount that they withdrawed, then r is going to be equal to b dot add the difference. I guess I'll if you know why he did this, let me know in the comments. Otherwise, I guess I'll go over it. I'll just trust you. I don't know. I'm not really sure. I think there has to be like a simpler way where you will simply, let's see, you would so this is something you need to do anyway. Then you check how much you have available. If this is not the case, then you need to withdraw, which you're gonna call withdraw. Withdraw will you're gonna call withdraw on this difference, which does make sense. And then given that difference, what are you gonna do? Given that difference, you will just you will send it. Yeah, you get R here. I think that may be a way to account for when you can't withdraw more or you can't withdraw exactly what's expected. And it may be a way to maintain a ratio, because otherwise here, instead of the R, you will just put like a ratio that you would get from shares. But for some reason, if B is less than R, then it just, I guess it works out to work in that way. And lastly, we get the get price per full share, which is equal to the balance multiplied by basically 1 with 18 decimals divided by the total supply. So this gives you what the price of the share is, which it's probably really useful to know so that you know how much it costs to get a share. Although if I don't believe it's ever used in the code. Yeah, it's never used. Although this may be the way to avoid this stuff. Although I guess we'll see in the controller if that's the case. So let's go ahead and check what the controller looks like. We're gonna go in contracts, controller, and we see the controller.sol. We have a bunch more of these Open Zeppelin code, safe math, ERC, etc. And we also have free interfaces. We have the converter, the one split audit, and the strategy interfaces. Next up, we have Safe ERC. We already addressed that. We have the address utility, which I don't believe we used in the previous code, but maybe it's used here. We'll see. But then we have Safe Math, and then we have governance and strategist. And strategist is the keyword for a person or a contract that is allowed to either rebalance or change the strategy. We have one split and rewards, which I'm not sure what they are. We'll have to figure out. And then we have vaults, strategies, converted. So vaults were the smart contracts we were checking before. Strategies is a set of smart contract we'll check later, and we'll probably check a couple. And basically, they define the way for you to earn your interest. And then we have converters, and which I'm not really sure what they are. Next, we have approved strategies, and this is actually a great opportunity to have a quick side tangent. The approved strategies are basically the reason why Yearn, and I know Yearn was hacked, and I'm not sure why. Maybe we can have a separate chat on that. But if I'm not mistaken, the idea of having approved strategies is the way in which you ensure that there are no strategies that would steal your funds. And that's actually how another protocol called Yearn Finance was hacked. So if you want to investigate that, you can actually go on rect.news, which is one of my favorite websites ever. And you can go on the leaderboard and you can see the records for contracts that lost funds that were literally stolen. You can see the Pickle of Finance is here. There's also an hack on Yearn. I guess let's just check what happened to Yearn. The vault was attacked using 9 flash loans. 11 million was lost from the vault, 2.7. Curve leafy. I think it was a Oracle attacked then. Falling victim to an arbitrageur must be believed for a team who were seen as unbeatable. Anyway, this is one of my favorite websites ever, and it literally shows you the evolving nature of DeFi. So if you're interested in figuring out why these protocols were hacked and you want to have nightmares about all of your money being stolen, definitely check those out. Check rect.news. Let's continue with our controller. We see a split set to 500 and then a max which is equal to 10,000. Our constructor will set the governance to the sender, as we said. Hopefully that was a multi-sig, which I believe it was. Then we have the strategies currently set to the message of sender. Then we have one split, which is set to an address. And then we have rewards set to a rewards, which is an address as well. For some reason, they chose not to add the one split to the rewards. I think because they didn't care, but for some reason they did this here and they chose instead to assign it from the constructor here. Then we have set rewards, which just sets the reward. Again, you need it to be done by governance. Same for the strategist, same for the split, same for the governance, etc. Then we have set vault. Setting the vault can be done either by the strategist or by the governance. And it will require that vault's square bracket token is equal to address 0. So that means that the vault that is assigned to this token needs to be empty. So I'm assuming this is a one-off setup that can only be done once. So you can only set a vault for a specific token once. And that's probably a pretty good idea to allow you to set that up later, so it's more extensible, but at the same time to avoid too much customizability, which may bring further risk on you. Next up, we have approved strategy. Approving the strategy will basically just set the token and the strategy. It's a mapping between the token and the strategy, and it's set to true. Very extensible, but it also ensures that you can have a strategy and a token pair assigned. But I'm guessing if you were to deploy a new strategy, we'll just deploy to a new address anyway. So it's just a way to ensure that the list of strategies is there. Then it allows you to revoke the strategy, setting that to false. That's fine. Then we have set converter. Set converter, again, can only be done by strategies or governance, and it will set the converters of input output to be equal to converter, where converter is an address. My intuition is telling me that this is a way to swap between different tokens, something like Uniswap or Curve, etc. But again, we want to keep in mind this converters keyword. Next up, we have set strategy. It requires that the strategy is approved, really important. And it will set current equals to strategy square bracket token, because setting a strategy requires the address of a token and the address of a strategy. So it will fetch the current strategy that is being used, and it will check if the current is different from 0, then it first will call withdraw all on the strategy. And that's because the strategy is the active part of the Yearn management system. And as such, you don't want to leave the strategy with a bunch of funds. They're going to be withdrawn. And then next up, we're just going to change the strategy, the active strategy for that token to be equal to the strategy. So this is nice. Next up, we have earn. We see that we receive a token and an amount. We have a strategy, which we fetch for the specific token. We have a want, which is given us by this, to us by the strategy, which is the want. And then we do, if the want is different from the token, so this is really important. If the want, i.e. what the strategy wants, is different from the token, i.e. what the strategy token is, then we're going to call converter, which is converter square bracket token square bracket want, keyword we looked up before. And then we're going to call ERC token safe transfer. We're going to transfer to the converter for the amount that we got as the parameter for earn. And then we're going to set amount to be equal to iConverter converter.convert strategy. iConverter.convert strategy. And then we're going to safe transfer want, which is the token that the strategy wants. And we're going to send it to the strategy. So what does convert mean? iConverter converter strategy. Let's check the interfaces on Yearn protocol interfaces converter. I guess I'll mark this. And then I'm going to search for iConverter, which we got from interfaces Yearn iConverter. And this is where I left off. Let's see what this iConverter does. Function convert address external result returns uint 256. I'm guessing it just converts, as in it just provides the ratio. It's just a way to calculate what each of them is worth. And safe transfer to converter, convert strategy. Or it's a way to, yeah, because you're sending the tokens to the converter. So I'm assuming it's actually a way to actually convert these tokens and basically swap them. So it's probably a way to generalize that. I'll have to check what this exact contract is to be sure, but I'm going to assume that that's a way to just swap tokens into that, which also explains that the fact that we have the check for want versus token, because in the case that want and token are the same, we're just going to send all of our tokens to the strategy. And lastly, we're going to call strategy.deposit. And as we said before, the difference between depositing, if you remember in the vault, you deposit without rebalancing because that way it's cheaper gas. So I believe that the earn function calls deposit here because this is not the cheaper transaction. This is the expensive transaction you want to have done to ensure that that works. And it seems like it's public and it can be called by anyone. I'm guessing because fundamentally you're doing a favor to the protocol by calling this function. So this actually will be called by a keeper, I'm guessing. And where keepers are a way to automate a bunch of tasks. And it's something that you'll definitely learn more as DeFi evolves. Next up, we have balance off. Balance off will check the balance of the token, and it will just get the strategy and then get the balance off of it. Then we have withdraw all, which will call withdraw all on the strategy. We're not sure where it's going to send these tokens to, but we'll see that. I'm guessing it sends it to this contract or to the vault, one or the other. But again, we'll see that as we get into the strategy code. In case token gets stuck, this will be literally the way to rug pull projects. In case token gets stuck, seems to actually allow any token to be fetched. So I'm assuming that this code assumes that this contract will never have any funds, because if it wasn't the case, then you would actually be able to rug pull the want token or the token from the vault at any time. So I'm assuming this controller is coded in a way where it will never have any code, because otherwise this is literally how you steal it. And the way you would prevent that would be to have a check between the token that the controller can hold and the tokens that the vault can hold, and you will just have a check to ensure that they're not the same. In case tokens get stuck, this is the way to, in case strategy tokens get stuck, seems to be a way to withdraw a specific token from a strategy. I'm guessing it's another utility of that type. Then we have the get expected return, which receives a strategy, a token, and parts. And it will return a amount that represents the expected. So let's see what that is. We have, and this is a view function, so it's you can call it, but it may also be used in the contract. So let's see what the balance, we're going to fetch the balance of the strategy. Then we're going to check what the strategy wants. And then we're going to do one split audit dot get expected return. And I'm guessing this is a way to figure out what the expected, basically what these strategies expecting to get. Or rather, this controller is expecting to get given the active strategy and the want. I'm not sure what parts is. It's just a number. So this is definitely something we'll have to investigate later. And lastly, we have Yearn and we have withdraw. Withdraw simply withdraws from the strategy. And then we have Yearn, and that was something really cool at the time. As you can see, it says it only allows to withdraw non-core strategy tokens, which is over the above and normal yield. And that was basically a way for you to do either a flash loan or a set of operations that are expensive. And if I'm not mistaken, there is an extra percentage fee on that. But fundamentally, let's see what it does. This contract should never have value in it, but just in case, since this is a public call, again, this confirms what we saw before, that the controller should never have a balance. Next up, we see before is equal to the balance of the token, balance of this contract of the token. Then we get we call withdraw on the strategy, and we check what we got after. Basically, we check, we withdraw from the strategy, we check the after. If after is greater than before, then we're going to get the amount that is going to be equal to the after minus the before. So this is the, let's call it the extra stuff that that we received from the strategy. We're going to get want from the strategy. So we know which token we want. Then we're going to set up this distribution variable set in memory as a list of uint 256. Then we're going to declare expected as another uint 256. We're going to call before, which we already declared here. We're going to just change it to be equal to IERC want dot balance address this. So we're going to get the balance of want that we currently have, and that's the before. Then we're going to do a safe approve on one split, which we don't know what it is, but we know that we are approving a way for safe split to do stuff. Then we're going to safe approve one split amount. So this is resetting the approval of one split to 0. And then we're setting it to a specific amount, which is equal to amount, which is equal to the difference between the before and after that we add up here. And now before has been set to this different value, which is the current balance of the want. Next up, we're going to set expected distribution by calling this one split audit dot get expected return. We have this expected and distribution. We're then going to call one split audit one split dot swap. This is the act of swapping. So this brings us, or at least it makes us think of Uniswap. And we see the expected and then the distribution here. And then we're going to have an after set to the balance of want that we now have in this contract. If after is greater than before, i.e. if we made some money, then amount is equal to the difference and reward is equal to the split divided by max. So I'm assuming this is a way to divide it to a certain percentage, and then we call earn on want on the amount sub reward, because we probably reinvest this balance and the other part gets put into rewards. So I think this reveals what rewards is. Rewards is probably a place where we store extra yield, extra results from doing this set of operations. And then earn is a way to basically reinvest, if I'm not mistaken. We checked it already. Let's see. Yeah, and earn is the way to basically convert and then deposit into the strategy. So basically, this is the code that runs all of the operations. The next code we want to check is the strategies code. I'm going to go in contracts, strategies, and we see that there's a ton of them. We're just going to check maybe one or two. I think the compound one is one of the best to check because we have an intuition for this. The compound strategy, and I'm seeing that there's curve compound, but the compound strategy is based on the idea that you can borrow or deposit and you can earn interest. And sometimes you can literally make more money in borrowing from compound than in actually lending to compound. And that's literally what the intuition is for the strategy. So we see that we have a ton of variables here. We want this token. We can check that on Etherscan. I'm not going to check all of them, but we can check at least the want so we know what this strategy wants. The strategy wants this token called CDI over CUSDC, which is basically the ownership of the CDI CUSDC pool. And then we have the curve, which is the smart contract for curve. We have the I'm assuming the Uniswap router contract. I'm also going to check this one. And that's kind of the beauty of having hard-coded variables, is that if you have the patience for it, you can, and this is the Uniswap router too, but basically if you have the patience, you can verify all of them. We have WEF, we have DAI, we have curve, we have gauge and voter, where gauge is, as far as I know, gauge is simply the way for you to stake in curve. It has this name, but it's basically the pool that you stake to in curve. Then we have the keep CRV variable. We have performance fee 450, strategies reward 50, withdrawal fee 0, and then fee denominator 10,000. So that means that, or at least that leads us to understand that the performance fee will be a percentage of this. So we'll just check it out. It's probably, yeah, 4.5% for performance and 0.5% for strategies reward. Next up, we have a proxy, governance, controller strategies. We already saw those. These are to ensure no shenanigans happen. And then we have earned, which is the lifetime earnings. This is just probably just a convenience tool to check what they earned. Then we have the event harvested, which shows you how much you earned and the lifetime earned. The constructor will set literally just like the controller was doing. Get name will tell you the name of the strategy. Strategy sets the strategy. We can set keep CRV here, which is an address, if I'm not mistaken. No, it's a number. Keep CRV, it's a number. Then we set the withdrawal fee to a number, performance fee, again, another number, strategies reward, and then we set proxy here. So these are just setters ruled by governance. Next up, we have a way to deposit, and depositing will do a safe transfer to proxy of the token that we want, and then it will call voter proxy.deposit into gauge and want. So this means that we will also have to figure out what this voter proxy is, and we're just calling this deposit function with the gauge parameter and the want parameter, where gauge is a address. There we go. And then the other one is the amount that we currently have in the smart contracts at the time of the deposit call. Next up, we have withdraw. Withdraw asset, controller only function for creating additional reward from dust. So again, you can only do it from the controller. Requires want, different from the others of assets. So this is the example that was mentioned about avoiding rug pulls. When there's a way for you to withdraw stuff and you're not expected to be able to withdraw because that has to be associated with removing tokens from the pool, you would have a check that ensures that whatever this asset is cannot be one of the assets that is related to the operativity of this. Because you could imagine that if I could withdraw the want, and then there is no longer any want in the strategy, that means that every person that deposited in their vault lost all of their funds, even though they still have the token representing their ownership of money that was stolen. So that's why you have these checks. This is like a very important thing. Next up, we do safe transfer from controller for the entire balance. Okay. Then we withdraw partial funds normally used with vault withdrawal. Okay. This is called, it's an external function, which means that it can only be called by another contract externally. So it can't be called from this contract. It has to be called by somebody else. Let's see, we have require message.sender. It needs to be the controller. We're going to get the balance of want from this contract. If balance is less than amount, then we're going to call withdraw sum. So this is just a way to, again, avoid extra work when you could just withdraw. Then we have the fee, which will be equal to withdraw fee divided by the fee denominator. You always multiply first, divide later, and withdrawal fee we said is a 0.5%. So it's a, what is it, 50 out of 10,000. Then we have the want. Here we're going to do a safe transfer from controller.rewards for the fee, because again, the controller.rewards is where we store the rewards. Then we get the vault by calling the vaults of others of want, and we ensure that the vault does exist, and that we do a safe transfer to the vault. So withdrawing from the strategy is the act of rebalancing, taking the fees, and then sending back to the vault. Then we have withdraw sum, and we have this voter proxy.withdraw. I'm not sure what this is. I'll have to check it. But basically, we're calling withdraw with the parameter gauge, want, and amount. I'm assuming it's a way to withdraw from the curve pool, basically. That's what I'm going to assume, although we will have to verify later. Next, we have withdraw all, which can all be done by the controller. It calls the function withdraw all, which with an underscore, which again calls the voter proxy withdrawal. And then it's going to check the balance of the want from this account. And then you're going to get the vault and then it's going to deposit to the vault. The fact that fetching the vault is done in this way basically creates this connection between the vault, the controller, and the strategy, where the controller is basically the pipings, is all the connections between everything else, while the strategy is kind of blind. It just asks the controller what to do, and then it sends the funds to the vault, because the vault is where you store all of the stuff. So that's great. Next, we have the harvest function, which is probably the most important one. So I'll talk about it last. Balance of want, just a way to know how much we have of what we want. Balance of pool, how much of this voter proxy is in the gauge. We'll figure out what this voter proxy is in a second, but that's basically what it does. Balance of is balance of want plus balance of pool. So this is the balance that we have. Then we have set governance and set controller, which are safe stuff. Next up, let's check the harvest function. Clearly, the bulk of this operation, again, can all be done by the governance or the strategist. We're gonna call harvest on this voter proxy. So we definitely have to figure out what this voter proxy does. Although I'm guessing it basically rewards. Harvest is the act of getting the reward. That's what I'm guessing at this point, but we'll have to verify. Next up, we get curve, IRC of curve, the balance of this. We check how much curve we have. If we have more than 0, then we're gonna call, we're gonna get this keep curve equal to CRV, which is the current curve we have, multiplied by keep curve divided by the phi denominator. So this is how much curve, this is a percentage currently of the curve we have. And we're gonna do ERC CRV safe transfer to voter. So we're gonna send the amount that we wanna keep, or this percentage of the amount we have, we're gonna send it to keep CRV, which I'm not sure what, to voter, sorry, which I'm not sure who is, voter. Then we're going to have CRV set to CRV minus the one we already sent. So now we have this new amount. And then we're going to safe approve and approve uni for 0, which means that we reset the allowance of the Uniswap router to 0. Next, we set that amount to this value up here, 150, on line 150. Next, we do path. Basically, we set up for a Uniswap swap. If you check the Uniswap documentation, this is exactly how they tell you to do it. And now.add 1800. I'm not sure if this is a way to do it in this block, but that's what I'm going to assume. And basically, we're calling swap exact tokens for tokens, where we put CRV and we expect a minimum amount of 0. So this may actually be part of how they got their funds stolen. I'm honestly not sure. I haven't. I remember checking it, but I guess I'll just speculate at this point. Complete speculation. But basically, if you set that the minimum amount you want for a trade is 0, that means that if somebody front runs you or that somebody manipulates the pool, you're gonna accept any deal. So that it may be a good idea to have the harvest set to only be called by strategies of the governance, because that way, they would have to listen on chain for when you're going to make this call. But this may be a way to basically give a worse rate to this contract, because there is no check here on how much it wants to get. Next, we have DAI equals to IERC DAI balance of address this. If there's more than 0 DAI, we're going to send the DAI to curve basically, and then we're going to call add liquidity with DAI set to that. So basically, we're going to reinvest some DAI if we do have it. I'm not sure why we mentioned DAI, but yeah, basically, if we have some DAI, we're going to reinvest. Next up, we have want. Basically, we're going to get the balance of how much we have. If we have something, we're going to then get our fees here with performance fee divided by fee denominator. Reward is the strategist reward. And then we're going to call we're going to send the rewards to the rewards set by our controller. And lastly, we're going to set the rewards to the strategist. And then we're going to call the deposit function only if we have more. So, and I'm guessing deposit was, just a way to put money in the voter proxy. And then it's going to call voter proxy.lock, which is definitely something to keep in mind, which means that in order to close our circle and figure out everything that we did, we have to check this voter proxy. And lastly, it just emits an event and it shows you that. So let's see what this voter proxy is. It's from Yearn voter proxy. From interfaces, Yearn voter proxy.sol. we see that we have a way to withdraw, we have a balance, we have a withdrawal, we have deposit, we have a harvest, we have a lock, we have a claim rewards. So I'm actually not sure why you wouldn't have the contract for the voter proxy. Maybe I'm not experienced enough to know. So that was kind of the entire flow of how Yearn works. Hopefully that was informational. As you can imagine, honestly, developing on Solidity is an extremely harsh learning curve, at least for me. And also the act of coding is not even the most important part, because the smartness of coming up with the strategies, figuring out these type of opportunities is way more, just way more complicated even than the code, even though the code is already complicated enough, and also extremely dangerous because you can lose all of your funds if you do it. So at this point, let's go and check the shitcoin like SafeMoon. So SafeMoon has a GitHub here, and they also have like a Twitter account that has over, and I have no idea how they have all of those followers, but they have 400,000 followers, and they seem to have raised like $700 million. So, no, $700,000. I'm not gonna expect them to have raised that much, but let's see what they're doing. Funding page, safely to the moon. 800,000 out of 1 million has been raised so far. Okay. Because they want to raise some money here. Okay. Anyway, if we look at the SafeMoon contract, you'll see that there's very little here. I'm not even sure why it's being forked so much, because this is literally the inline version of a. This is just the inline version of a ERC20, and then there's some Uniswap code. So it's not. There's nothing particularly unique. There's actually nothing unique about this. But anyway, this is the worst way to read the code, because all of your contracts are here. But I'll try to do the best that I can to do that. And the reason why you will do it is because it's submitted to like a contract verifier that doesn't either doesn't use hard hat, or it's just it is what it is. Next up, let's see. We see SafeMoon features 3% out of fee auto add to the liquidity pool to locked forever when selling. 2% fee auto distribute to all holders. I create a black hole so BE token will deflate itself. 50% supply is burned at start. Okay, let's see that. So first of all, we have the interface for IRC20, the ERC20, and you can literally get that from the Open Zeppelin code. This is 6.12, which means that they're using version 3 of the Open Zeppelin code. But yeah, it's a very safe code. We have the safe map function. We cover that. And this is, again, a copy paste of the 3.0 version of that. Then we have the context. Yeah, this is basically a way to get the message sender and message data. Although I haven't never seen this one used, but there's probably somebody that has used that as well. But yeah, I've seen this used a lot to get the message.sender with this function underscore message.sender. We have the address library, which, as I said, checks for contract. It basically verifies that the sender is a contract instead of it being a personal wallet. Then we have send value, which I believe just sends funds. And function call. These are ways to interact with contracts programmatically. Then we have the ownable. So anytime you see ownable, you want to think of owner. You want to think of what's it called? Governance. This is basically the way to have the owner. We also see a lock time. But yeah, this is just the ownable contract, which again, you can check here in the, I think in the utils. In the case of 3.x, it's going to be in access control. So you can check that. But basically, if it's ownable, you own it, and it just provides an extra security. Next up, we have the V2 factory, which is the way to set up pairs, right? You have get pair, all pairs, create pair. Is basically your way to register your new pair to Uniswap. Then we have the Uniswap V2 pair, which is the specific pair, which if you're not aware, a pair is the way in which you specify how two tokens can exchange. And the most notable stuff is that you're going to have a ratio, which is x times y equals k, or a curve, I guess. And that basically determines the price of each asset at each time. Then you have the Uniswap router V1, and that's the basically the contract. This is the V1. There's going to be the V2 later, but this is the contract that allows you to specify how to perform trades. So you have all of this function. You have the if, and basically this is why developers hate if and love WEF, is because when you have to deal with if, you have to write twice the code. So now we have the Uniswap router V2, which is the more sophisticated version of the router, and it's the latest router, although there's a V3 coming out soon enough. Next up, SafeMoon is context. Basically, SafeMoon, this is the declaration of the SafeMoon contract. SafeMoon is context, IRC, and ownable. It uses SafeMath. It has an address. We see R owned to owned, a mapping between addresses and amounts. It's going to be private. We also see the allowances. That may be because they are hard-coded is ERC20. Is excluded from fee. Basically, there may be somebody that doesn't pay fees. Address is excluded. Then we see max is going to be equal to tilde u int 0. The total is equal to whatever this is with 15 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 plus 15. 24 zeros. Okay, so there's going to be 1 to the 1e24, I guess. Yeah, 1e24 is going to be the total distribution, I'm guessing. So it's basically going to have 24 zeros, which is a million if basically it would be a million with 18 other zeros. Then we have the R total, which is equal to max minus max modulo the underscore T total. We'll see what this is. And then we have the T fee total. We have the name, symbol, decimal. There's 9 decimals. Pretty odd. But basically that means that there's, what is this again? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 and 6, it's 15. There's 15, 1 to the 10 to the 15 of these tokens because the decimals are 9. Tax fee is 5. Previous tax fee is underscore tax fee. Okay. Liquidity fee is 5. Previous liquidity fee. So I'm not sure why this would be set up in this way, but it's, you know, it is what it is. Then it declares a swap, Uniswap router. It gets a immutable pair, and that's why I'm confused, because you will just do immutable here as well. But you know, whatever. In swap and liquify is a Boolean, and then they set public swap and liquify enable set to true. Max transaction amount is this number right here. Number sell to add liquidity is this number right here. Then they have event min tokens before swap updated. Swap liquify enable updated, swap liquify. And then they have a modifier lock the swap, which checks if in swap liquify is true. And then it will set the in swap and liquify set to false. Okay. So this is just, you know, just weird. I don't really have much to say on this. R owned is equal to, okay, R owned of message.sender is equal to the total. So this R owned is setting the balance of this guy to everything I'm seeing. Then I'm seeing Uniswap router, and they're setting it to this thingy, which you would have to check on the Binance Smart Chain Explorer. Basically, this is the router. I'm guessing this is going to be PancakeSwap, but we'll see. BSC Explorer. Yeah, this is the PancakeSwap router. Makes sense. And factory Uniswap V2 pair is going to create a pair between this token and WEF, where WEF is the BSC coin. And set the rest of the contract variables. Is excluded from fee owner. Owner doesn't pay fees. Is excluded from fee address this. This contract doesn't pay fees either. And then it's gonna emit transfer to address 0 of message sender and total. Address 0, message sender total, but our owned of message sender is equal to our total. Okay. And then you see the classic ERC20 methods: balance off, transfer allowance approved, transfer from, decrease allowance, deliver, function deliver will get the message.sender. It cannot be excluded. So there's basically a blacklist here. And then it gets this R amount from get values, which we'll have to check. And then it sets our own sender equals our own sender minus sub amount. So the sender, the guy that makes the request, basically owns less because they're sending it to him, I'm assuming. Our total is our total.sub our amount, T fee total, add T amount. They're going to increment T amount. Where T amount is delivered. They're going to increment the fees to T amount. They're going to reduce the total R by R amount, which is from get values. Then you have a reflection from token. T amount is a variable that is received. It needs to be less than or equal to T total. Amount must be less than supply. Okay. Deducted if you're not gonna deduct transfer fee, which I'm assuming it's a global variable, then you're gonna get R amount and you're gonna return that. Otherwise, you're gonna get values and return transfer amount. Token from reflection. Let's see what this get rate function and get values is. Get R values, get values. Transfer amount, get TV values. T fee, calculate tax fee. T liquidity, calculate liquidity. T transfer. Transfer amount is going to be equal to T amount dot sub T fee dot sub liquidity. So I'm guessing it's just a way to handle a ratio. As they were saying it, this is like they're trying to do a deflectionary thing. But yeah, it just doesn't look. And then they have swap and liquefy. I guess I'm just more confused by this than I would expect. If you have specific questions, I'm gonna take a few specific questions, and maybe I will study the code and give you a definitive answer. But yeah, I wouldn't recommend investing in this at all. And I would also recommend new developers to start using Hardat, which will handle your contracts in a cleaner way. So you don't have to inline them. You can just use the Hardat verify plugin to verify your code, and that's going to make your life so much easier. So let me know if you enjoyed the video. I thought I would try something new, and so let me know how that goes, and I'll see you soon. Thank you for watching.